Hello and welcome back. So now let's run the simulation. Okay, so I'm going to run just the turbulent case. Okay, so remember that here in the problem definition I'm asking you to run also laminar. Okay, it's up to you. The workflow is exactly the same. So let's launch any of these meshes. So I will launch the structure mesh, this one. Okay, so I will double click here and this will launch Fluent. Okay, so Fluent, okay, see that Fluent can run 2D and 3D. So here by default, it knows that the geometry is 2D, so it will select it. If you are outside the workbench, you need to select this one, we're going to see later. Then you have this option. I always recommend you to choose double precision. Okay, I don't see any reason why not. So choose double precision. Later we'll show you a video, the difference between double and single. And then here you have the number of processors. Okay, so according to the number of cores that you have in your computer, put it here. So in my case, I have 4. And press start, and it will launch Fluent. Then do not select GPUs. Okay, I don't like that one. So probably GPUs also will give you an speed out, but they have limitations. That depends in the graphic card that you have. And most portable computer they don't have a good GPU or a powerful GPU with a lot of memory. Okay, so see that is reading mesh, everything. So you have, so one thing that maybe we're going to have different windows already set predefined stuff here, but again, you can arrange everything. So here you see that you can go, okay, you hide the ribbon there. And here you have many options that you can explore. And here, but it's interesting to see that you can choose how you want to arrange your windows. So see default. So probably if my window was different from what I have, or you have something different, let's put everything here default. I always recommend you also press there and you have the help. So use the help. You have access to the online documentation. I will show you. It's very good, the help. Fluent. So I always recommend you go here and see that you will have the theory, okay, user guide, you have access to some tutorials. So I invite you to read the documentation and if you want to know some actions, okay. So see here the wheel, zoom in, zoom out, middle button, just pan. Those you can play with Control Shift, options to rotate, stuff like that. So that I leave it to you to play. So here you can select that, okay. So at this point, let me set up the case. Let me put this also reset. Okay, I rotate everything, so I don't recall how to reset my window here. Okay, bam, bam, bam. Okay, for the moment, I think I will leave it. So I did it, I rotated by... Okay, now view here, and let me go views. Okay, here, apply, my front. Okay, so I have the window. So remember that we have talked about the case setup. You do it here in this vertical workflow. So you can do it also here. You have this ribbon and you have many options, but I like to work in the vertical here in this vertical workflow. So we start here, general. You choose general physics, general options about your solver. So let's use pressure-based solver. So you have 2 types of solvers. Pressure-based are okay. So both of them are okay, and stay with the pressure base. We are going to run a steady simulation, and we don't want to use any of this axial symmetry. Okay, you have more options. Okay, but leave it like that. Then models is here where you enable models. So for the moment, we're focusing turbulence modeling. So as you go to the tab viscous, here's where you can select models. Okay, so if you want to run the laminar solution, laminar means no turbulence model. Okay, select there. Okay, so by default, you're using this turbulence model, the K-SST, which is the one I recommend, and also you see Fluent proposed by default is the most, let's say, most general one. Okay, you don't have to set up any more models. So then you move to materials. So you have Fluent and Solid. Solid, you don't need to set up anything because Solid you use it when you're doing structural computations or conjugate heat transfer. So here we're not doing that. So it will take a default value, but it doesn't use it. You just need to define your working fluid. So you go here, materials, double click air, and you can choose your properties. So as you recall our problem definition, I'm asking you, so we're using dynamic similarity, so this is an incompressible problem. So we can play, we know that the Reynolds number is the only parameter. With that single parameter, we can control everything, okay? So I'm asking you set density to 1, inlet velocity to 1, we know the diameter, and we want to set this value, okay? This. So basically put it 1, okay, for that, and for that Reynolds number, my viscosity will be that, okay? So let me double check. Yeah, I think. Okay, it's 6. Okay, so this is for a Reynolds of 100,000. Okay, so put it there. Okay. And then we move here. Okay, here we don't need to set up anything for the moment. Okay, then boundary conditions, and here you see the names that you gave when you were creating the mesh. You put it here. So we go inlet, you know which one's your inlet. Okay, so you select there, and then see that we want to set, you have different types. Okay, you can put pressure inlet, velocity inlet, mass flow, but in our case, let's set up the velocity inlet. And we want magnitude, normal to boundary, so you have different options. So magnitude, normal to boundary is okay. 1, put it there. And then see here that you need to give boundary condition for the turbulence model. So we saw this in the theory. Okay, so in this case, I will choose this intensity. So I will put, let's say 1% intensity, and this one I know is 0.01. Apply. And you are all set. These tabs here, they are related to models. So if you put compressible flow or temperature, you will have that one. For the moment, we don't need those actions. And the same for the outlet. So the outlet is a pressure outlet. Edit. And in this case, you need to set up much here. So it's here that see that you fix the pressure. This is a 0 gradient. You fix the pressure at the outlet, okay? So we're fixing the pressure, these options are okay. And this one, again, we choose similar values to the one in the inlet, okay? So this option, see that is called backflow. Backflow means that it might happen that you can have flow coming back into your domain. Now, if you have vortices or separation. In this case, I know that we don't have, but in case that you have that, this is how you control that. This is a specific treatment to avoid that. Usually you set the same value of the inlet. Okay, so we set that one to pressure outlet. Then symmetry, it is a symmetry. Okay, so it has been chosen by default already. Okay, so, and then wall. Okay, also the wall was chosen by default, but if you want to change it, you change it. Okay, so also Fluent is clever enough to know, according to the names that you give, you call it an inlet, likely will put velocity inlet. You call it outlet, will call it pressure outlet. You put scene or symmetry or similar names, it will by default put symmetry, but then also you can do that selection manually. Okay, so we have all boundary conditions. So now these options, these are advanced options. We don't need to do anything here, anything here. Reference values, let me stop here. So remember, these reference values are those values used to compute coefficients. So you have like lift, drag coefficient, friction coefficient, turbulence intensity. So these are the quantities, all the non-dimensional values that you compute. These are the quantities that you use to normalize all those values. Okay, so you put here your values. It's up to you. So usually what you do is that to normalize all non-dimensionalize or your quantities, or to compute those coefficients, we use free stream values. So I know that I can go use from the values from the inlet. No, I know that the inlet is my free stream values, and using this value, it will compute everything. We'll put those values there. Okay, so using these values, it will normalize everything, but it's up to you you can also insert all these values manually. Reference frames, nothing to do. Name and expression, nothing to do here. So now we move to solution. So see that this is your case setup. Okay, so now we move to solution. So in the solution, we choose the solution method. So see that Fluent is already proposing something. So I recommend you to use what is Fluent proposing. Okay, later we have another tutorial that are going to show you a little bit basic numerics, but this proposal, now this is what this solver that Fluent, this method that Fluent is proposing initially is very good, it's very robust. Okay, so just take these actions. What is important here also, I want just to remind you that momentum, this should be always second order, okay? If you choose first order, this is too dissipative, okay? First order will always give you a solution, it's very stable, okay? But if you put it in the momentum, that is too diffusive. It is unacceptable for production runs, so at least second order. So everything second order, quick, all these are high order, this is the only one first order, so just to make that remark there. Controls is also related to the solver, so use the default options, okay, for the moment. And here, report definitions is where you can create monitors, okay? So remember, it's a good idea to monitor like mass flow or the Y plus value. So it's here where you do that. So let me create that monitor here. So you right click here, see that new, you have many options, okay? So it's up to you to play around. So for instance, let me create one for the mass flow. So I know that I have the flux report here, and I will mass flow rate, okay? I will call it here imbalance, and I want to compute the mass flow between inlet and outlet, okay? So you select there, report to plot, okay? You can also report to a file. So you select there. So let me select it here to show you that it will save this in ASCII file, and then you can open that to plot or post-process data. It's up to you. So, okay. And you have this monitor there. Okay, so you see that you will have the plot and files. And now let me create another monitor to monitor the Y plus. We have seen that that is a very important quantity in turbulence modeling. So you have a surface report, and I want to compute the average. So we talk about also that we want to monitor is the average value, okay? You can also monitor the maximum. For the moment, I will create just a monitor for the average. Okay, so one you can create also for the maximum. Phase average, where do I want to monitor? At the wall, what quantity do I want to monitor? Choose here the quantity. So the Y plus, you're going to have it in turbulence. Here, Y plus. Let me give it a name. We'll call it Y plus. And I just want to plot. I don't want to resave the file. Okay, and you have it there. So plot, okay, and you are ready to go. CellRegister, so we move here, nothing to do here. This is advanced. Initialization. So now we need to initialize. So remember, we set boundary conditions. Now we need to give initial conditions. So you have hybrid initialization, which probably I recommend you to use. Okay, so this Fluent here will use a specific method to find the best boundary conditions. Okay, so I recommend you to use that, but in this case I will use the standard initialization. So I will need to give those values manually. So if I go here, compute from the mean values at the inlet, see here that is computing these values. And as you recall the lecture about turbulence estimates, as you go there, you will see that how you can compute the turbulence estimate, and you will see that we get similar values. Okay, again, as you go to the help, you have the help here, you will see all the equations, correlations implemented in Fluent. Okay, but basically these quantities here are computed using correlations similar to the ones that we saw in the lecture 4. So press initialize, and now the problem has been initialized and we're ready to run. Okay, so also remember, every now and then save your solution. So we're saving everything, and at this point let me run. Okay, but then we have calculation activities here. We don't need to do anything, but here you have options to stuff like automatic save the solution every, let's say if you want to save the solution every 100 iteration, put here 100 iterations. Very useful. Okay, in this case I'm not going to do it, but if you are running really long simulations, it's a good idea to give a saving frequency. Okay, so here you have more options, the quantity of files that you want to retain. So usually I'd say like this: retain the last 2 files and save every 100 iterations. Okay, and you have more options here that we don't need to use for the moment. Okay, at this point, run calculation. Okay, so this is the parameters to control the iterative margin in this case. So here, the only thing that we need to say is the maximum number of iterations. So I will put 1000. So what is going to happen, the solver will run up to reaching this number of iteration or until reaching convergence. Where is defined the convergence? Is you go here into monitors, see here residuals. Here's where you have your absolute criteria for each equation that you are solving. So when you reach this absolute criteria, it will stop, okay? Whatever happens first. So usually most of the time you reach this in steady simulations, okay? So at this point, we're done. Press calculate and see that it will start to plot the information. You see that this is imbalance. Okay, flow imbalance should be, the method is conservative, so this imbalance should be a low value. See the y plus at the wall, see that is close to that estimate that we say that we want something close to 1, about 2. And here you have your residuals, okay? So when you reach this 10 to the minus 3 mark, it will stop. I would like to say something later. We're going to work with a steady simulation, but not necessarily. The fact that this residual doesn't reach, they don't reach the your final tolerance doesn't mean that your solution is convergent. Okay, that is just an indication that you have some unsteadiness. Okay, so not necessarily they need to reach that tolerance that you are given. Okay, and that happens rarely actually. So in this case, it's a pipe flow, it will happen, but not necessarily they need to reach that tolerance. See that after 128 iterations, it has reached that tolerance. And see that you are monitoring the imbalance, and this is important, okay? So as you see here that this imbalance is a large value, or if it is oscillating a lot, you might need to run this simulation for a longer time, okay? And also Y plus, see that is already stable. So it's not, you don't need to, it's not only looking the residuals, always monitor global quantities, okay? And if these global quantities are oscillating, it's better to keep this solution running. Do not believe in this one, or don't take this one as the absolute criterion to stop your simulation. So let's say that in this case you want to run for a longer time. What you need to do, or reduce the tolerance, or switch off the monitor. So you go back to residuals, you can reduce this value. So let me reduce it to 0.5, or you can switch it off. Okay, so you put like this, it switch off. So it will run until the maximum number of iterations. So I will do like this, and it will run a little bit longer until reaching that tolerance. Okay, see that now, boom, stop. So we're ready, we're done here, and you have the solution. Now let's do this. Let's look at the colors. So let me show you fast the colors here. So as you go here, contours, save display, here you can choose whatever you want to visualize. Okay, so you have velocity. Okay, so you can zoom in here. Okay, so you go here and see that at the wall you have your boundary layer and the profile is developing. So you have everything here, to all the turbulence quantities. So we have seen what is K, we have seen what is epsilon, omega. Okay, so we can have an idea what is happening there. Okay, so visualize everything there. So at this point you are there. For instance, you want to save figures here, you have here this option. Okay, copies, no, here, this one, and you can save the figure. Okay, then also you can plug vectors. Okay, so you go there, be careful that is you have a lot of cells, and if you press save display, it will put a lot of vectors, so it might crash your screen. So usually put here a skid, and will skid like every 4 vectors, or you are plotting less information. So you see here the effect. So be careful that sometimes happens that you have a lot of cells and this crash. So you have your vectors there. And there is more complicated stuff that we're going to do it when we're outside of the workbench. Okay, you can also do it in the workbench, but I would prefer to move outside of the workbench to do that. Okay, but this is the basic simulation setup. So you have seen how to run. So now feel free to run also laminar case and everything. So at this point, let me close here. So are you sure you want to click the use? Okay, okay, so here it's asking you the settings. So see that you did as a top of the case. So the settings that you have, you want to use it for future simulation, yes. Okay, so it's saving a setting file. Okay, and it's saving. So I think in my case it's giving me this not responding. I think it crashed in my case. And you have the case. Okay, so now we can do exactly the same setup that we did. You can do it in this mesh. Okay, so you have the other. So actually in my case it crashed. Close program. Okay, I don't know what it crashed. So that's why I told you that every now and then save the case might be the case, might be that it crashed. So now if you want to run with the unstructured mesh, just go and do the same setups. Okay, so something important that maybe you would like to do the same setting that you did here in the second case. So to do that one, see that you have this file here set. This is the settings that you have here, that you did here, that you can read here. Okay, so let me show you how. So see that you have the location there. Okay, so let me go and open this one. It's always double precision. So now you need to set up everything and do everything that we did. So this setting file have all the configuration. So I will show you. And see that this file here you have the, okay, let me open there. There you have the output file of the imbalance. So now in this case I'm using this program, and see that you have iteration number and imbalance. Okay, so now you can plug this using your favorite software, okay, whatever you use. Okay, so I read the mesh, see that you have the mesh. So to read the settings, okay, you go here and should be journal solution files. Okay, so save picture preferences. Okay, file. Okay, read. Should be journal, maybe. No, it's not journal. File, read, skin. No, skin is something else. So if I go user define units, custom, function hooks, solution results. I usually I don't recall where they put that option. Okay, should be somewhere here where I lost that option. Let me click here. So you have read, profile, autosave, import mesh case, project, inside, plot 3D, partition, interpolate, save picture. Okay, I don't see the option, but to read that setting files, see here, this is called the text user interface. You press enter, see that you can input commands here. So as you press file, you enter into this directory, you press enter. See that you have the option read settings. This is what you need. You read that setting files and you will set up the case automatically. So let me go ls and see that you have the settings there. Okay, so let me go read settings, and it will ask you what is the name of the file. sys1.set, and when you read that, it will apply that setup into this case. Okay, so see that now you have all the automatic setup. So everything that you did previously have been done in this one, and you are ready to go. Initialize, okay, and I go here, okay, and calculate. And it's running. Okay, so my previous setup, you put it there. If I stop there, so that option is very powerful. Okay, Okay, probably, okay, my settings, I read an empty setting, so let me go back to show you better here. So you need to take Fluent and see that this is the setting of the previous case, and I want to use that setting in my current case. So let me put here, okay, sys set. Okay, so read settings, and it's sys set. Okay, now I read that settings. I have everything, initialization. Okay, go there. And now I have the right settings. So that option should be somewhere here, but I don't recall where you have these settings. But always go here and see that when you set up one case, and in that case that you set up here and you run, is you have in that case the setting files. You can use this into other case. So just simply you just need to move files. So you have the option open. You open a folder there, copy that, and then move that file into the other case. Okay, so you have the other case, and you move to the other case. So usually the other one, you would go here and just put it there and open. But see that this is a little bit tricky when we're outside this bubble of the workbench. Since are easier, and we're going to move to that one just to show you. So in this case, let's wait until the simulation, this one is done. So see that actually the convergence seems to, there's a convergence rate, different convergence rates, as you can see. Probably this one seems to be that is a little bit better, this convergence. Okay, so it's difficult to assess, but it's very smooth. Okay, so we have our imbalance, so everything seems to be stable. The y plus is already stable. Okay, and residuals are there. Okay, and at this point we can visualize the solution. Plot there, and let me choose velocity, and here we are. Okay, you have the same post-processing as previous. Nothing changed. So with this, let me end here. So okay, let me close here, close Fluent. Okay, choose that one. Okay, let's see. I hope it won't crash like in the previous one. Okay, it didn't crash. Close there, and see that save. Okay, let me save, and we're done. You have all the cases here. You have on your directory structure, you have everything. Okay, so whatever you put the files, you go here, you can sort, and you have the files. So something about the Fluent files, just to make it clear also. So you see here that you have a case file .cast.ha. Here you have the mesh with the case setup, and in the .dat, this is the solution. So here it's telling you that you have a solution now in the iteration 100. So this is case setup and mesh, and this is the solution. And when you were generating the mesh here in sys, this one is the mesh, is the clean mesh. You don't have case setup here. So this is a clean mesh, no case setup. The .cast.h5, in this one, you have mesh plus case setup. Okay, so now you can copy this one and put it outside and do the setup there. So this is all for this case. This was in the workbench. So the next video tutorial, let's move to outside of the workbench. Okay, so we're going to do pretty much the same. We're going to start from a case that we already run. Okay, I'm not going to show you all this stuff, but now I'm going to show you how to run outside workbench and how to do more advanced post-processing. So we're going to do these plops. Okay, I'm going to show you this. So thank you for your attention. See you next video. Bye.